Right now, as you sit in your room, you are moving. The coffee in your cup is perfectly still, its surface a mirror. The air around you is quiet, and the floor beneath your feet feels like the most solid, unmoving thing in your life. But that is an illusion. Right now, you and everything you have ever known are travelling at roughly 1.4 million miles per hour toward a target you cannot see. In the time it took you to hear those first few sentences, you have already travelled more than 600 miles through the deep, cold vacuum of space. You cannot feel this motion because the pull is so vast and so consistent that it has become part of the background of your existence. But the universe is not still. It is a place of violent, invisible migration. And the most unsettling part of this journey is not the speed, but the realization that we are moving through a minefield. For decades, we looked at the sky and saw a garden of light. We saw stars, planets, and the glowing dust of nebulae. We assumed that if something was dangerous, it would at least have the courtesy to glow. But the data now tells us something different. Scattered throughout our galaxy, hidden in the dark spaces between the stars you can see, are hundreds of millions of invisible predators. Scientists call them rogue black holes. To understand why these objects are so unsettling, you have to look past the science fiction tropes of space vacuums and look at the measured reality of a stellar corpse. A typical stellar mass black hole is not a large object in terms of volume. In fact, if you were to stand next to one, it might only be about 15 to 40 miles wide, the size of a small city or a large island. But inside that tiny diameter is the mass of 10, 20 or even 50 of our suns. Imagine the entire Earth being squeezed down until it is only 2.5 centimetres across, the size of a single grape. That is the level of density we are talking about. At this scale, the ordinary rules of matter don't just bend, they evaporate. These objects are the corpses of stars that died in such a violent collapse that they broke the fabric of space itself on their way out. The mystery scientists can't fully explain isn't just that they exist, but that they are wandering. Usually, a black hole is anchored. It sits at the centre of a galaxy or remains locked in a binary dance with a living star, slowly feeding on its companion's gas. But sometimes a star dies in a lopsided supernova. The explosion is so powerful and so uneven that it acts like a cosmic kick, launching the newly born black hole across the galaxy at millions of miles per hour. These are the rogues. They have no home. They have no orbit. They are simply drifting through the Milky Way like invisible shipwrecks. This is not speculation. It is something multiple independent teams have now confirmed. In 2022, astronomers detected the first definitive rogue black hole just 5,000 light-years away from Earth. It had likely been drifting through the darkness for millions of years before we noticed it. But how do you see something that, by its very definition, emits no light? Imagine you are looking at a field of grass on a perfectly still day. You can't see the wind, but you know it's there because you see the grass ripple. Searching for a rogue black hole is like that, but on a scale that defies human intuition. As these invisible giants drift, their gravity acts like a lens. If one passes directly in front of a distant star, it warps the star's light, stretching it into a ring or making it briefly appear much brighter than it actually is. This is called gravitational lensing, and it is the only way we can find them. The mystery that keeps physicists awake is the sheer number of them. Estimates suggest there could be 200 million of these rogues in our galaxy alone. Because they are invisible, we have no way of mapping where they are or where they are going. We only know they are there when we happen to catch them rippling the light of a star in the background. Right now, a rogue black hole could be entering the outer edges of our solar system, and we might not know it until it starts to tug on the orbits of the outer planets. It wouldn't need to swallow the Earth to end our world. It would only need to pass close enough to pull us out of our stable orbit around the Sun. We are moving through a galaxy filled with millions of invisible high-velocity traps, and we are doing so with our eyes essentially closed. It is a realization that carries an immense existential weight. The universe is not just indifferent to us. It is designed in a way that makes its most dangerous residents almost impossible to see. This is the first of 10 mysteries that challenge our understanding of our place in the cosmos. If you enjoy these kinds of deep, measured investigations into the nature of reality, you should subscribe now. The investigation into what scientists can't explain is only just beginning, and it leads us from these drifting rogues to giants so large they shouldn't even exist. The investigation starts with the giants. If the rogue black holes we discussed are the silent, drifting shipwrecks of our galaxy, then the mystery we are about to encounter represents something entirely different. We are moving from the invisible predators of the present day to the blindingly bright monsters of the deep past. To understand the second mystery, you have to look further than any rogue star ever travelled. You have to look back to a time when the universe was still in its infancy, a period astronomers call the toddler phase of the cosmos. Imagine you are looking through a telescope that has the power to see not just across space, but across time. As you peer deeper into the darkness, you are looking at light that has been travelling toward you for 13 billion years. This light was born when the universe was less than 5% of its current age. At this point in history, the first galaxies were just beginning to huddle together out of the primordial mist. Logic tells you that in such a young, chaotic environment, everything should be small. The stars should be first-generation infants. The galaxies should be thin and unformed. And the black holes? They should be tiny. But when scientists pointed our most powerful instruments, like the James Webb and the Hubble, at these distant reaches, they didn't find infants. They found giants. This is the chronology problem. It is a mystery that suggests our understanding of how the universe grows is fundamentally broken. To grasp why this is so unsettling, we first have to talk about how we found them. For decades, these objects were a ghost in our data. In the early 1960s, astronomers began detecting radio signals from what looked like ordinary stars. But when they analysed the light from these stars, the results were incomprehensible. An astronomer named Martin Schmidt looked at the data and said it looked like gibberish. The chemical fingerprints of hydrogen and helium, the very building blocks of the stars, were in the wrong place. Eventually, Schmidt realised the truth. The light wasn't wrong. It was just incredibly red-shifted. The objects were moving away from us at fantastic speeds because they were billions of light years away. These objects are now known as quasars. A quasar is not a star. It is the most powerful sustained engine in the observable universe. It is the bright, screaming accretion disk of a supermassive black hole that is feeding so voraciously that it outshines every single star in its host galaxy combined. Now, here is the problem that keeps physicists awake. When we look at these quasars in the very early universe, less than 1 billion years after the Big Bang, we see black holes that have already reached a scale that defies human intuition. We are seeing behemoths with a mass of 40 billion suns. 40 billion. Let's humanize that number, because at this scale, the zeros start to lose their meaning. If our sun were the size of a single grain of sand, a black hole with 40 billion solar masses would weigh as much as 10 large dump trucks filled to the brim with sand. Imagine a single object compacted into a space not much larger than our solar system that carries the weight of 40 billion stars. According to every model of physics we have, these giants shouldn't exist yet. The reason lies in a fundamental law of the universe called the Eddington limit. You might assume that a black hole can eat as much as it wants, as fast as it wants. It's a hole in space, after all. But the universe has a built-in speed limit for growth. When a black hole feeds, it creates a traffic jam. As gas and dust spiral toward the event horizon, they rub together at half the speed of light. This friction generates heat, millions of degrees of it, and that heat produces light. This is the light we see as a quasar. But light has pressure. It carries force. As the black hole tries to pull more gas in with its gravity, the intense radiation blasting out from the accretion disk pushes that gas away. It's like a person trying to walk into a hurricane. The wind is pushing you back just as hard as you're trying to lean forward. This creates a stalemate. If the black hole eats too fast, its own brightness quenches its growth by blowing its food away into deep space. This speed limit is the Eddington limit. And based on this limit, it takes a long time to grow a giant. To get from a small stellar mass black hole to a 40 billion sun monster should take billions of years of steady, uninterrupted feeding. But we see them fully formed just 500 million years after the Big Bang. This is the cosmic equivalent of walking into a nursery and finding a newborn baby that already weighs 500 pounds and stands 6 feet tall. It is chronologically impossible. This is not speculation. This is a recorded, measured contradiction in our sky. Scientists are currently struggling to explain how these early giants bypassed the speed limit. Did they start as seeds that were already massive at birth? Some theories suggest that in the dense, hot environment of the early universe, massive gas clouds skipped the star phase entirely and collapsed directly into black hole seeds that were 100,000 times the mass of the Sun on day one. But even then, the math barely works. The existence of these giants suggests that the early universe was a much more violent and efficient place than our current theories allow. It suggests that there are ways to bypass the laws of physics that we simply haven't discovered yet. Every time we look at a 40 billion solar mass quasar at the edge of time, we are looking at a monument to our own ignorance. We are seeing something that tells us the clock of the universe might not work the way we think it does. And as unsettling as these early giants are, they lead us to a deeper, more mechanical question. If a black hole can't eat fast enough to become a giant, perhaps it didn't eat at all. Perhaps it was born from a vortex that ignored the stars entirely. That leads us to our next mystery, the concept of the direct collapse. But before we descend into that vortex, take a moment to consider the scale of what we are discussing. You are standing on a planet that is 4.5 billion years old. You are part of a species that has only had telescopes for 400 years. And yet, we can look back and see that before the first galaxies were even finished forming, the universe had already created its most powerful and destructive residents. The early giants are the sentinels of the deep past, and they are telling us that the story of our beginning is much stranger than we ever imagined. If you are finding this investigation into the impossible scales of our universe compelling, make sure you are subscribed. The mysteries only get deeper as we move from the mass of these giants to the terrifying way they were born. The investigation continues with the vortex mystery. We have reached a point in our investigation where the math no longer matches the reality we see in our telescopes. As we discussed in the previous chapter, finding a 40 billion solar mass black hole in the early universe is a chronological impossibility if we follow the standard rules of growth. If these giants had to eat their way to that size, they would have needed billions of years of steady, uninterrupted feeding, time they simply did not have. This leads us to a conclusion that is, in many ways, more unsettling than the giants themselves. If the path to the giants is blocked by the laws of physics, then we have to consider that the path itself is fundamentally different. We have to consider that some black holes did not grow into giants. They were born that way. To understand how this is possible, we first have to look at the standard way a black hole is born, the process we have observed millions of times in our own cosmic neighbourhood. In the modern universe, a black hole is the final, desperate act of a dying star. Imagine a star dozens of times more massive than our Sun. For millions of years, it exists in a state of violent equilibrium. Gravity is trying to crush the star's trillions of tons of gas into a single point, while the nuclear furnace in its core is pushing outward with equal force. It is a stalemate that lasts for eons, but eventually the fuel runs out. The furnace shuts off. In less than a second, faster than your nervous system can even register the concept of a change, gravity wins. The entire mass of the star comes crashing down toward the centre. It hits the core with such force that the outer layers are blasted away in a supernova, while the core itself is crushed into an infinitely small point. This is the star phase. It is a slow, multi-million year journey from a cloud of gas to a star, and finally to a black hole. But this process has a built-in limit. A single star can only be so big. Therefore, the black hole it leaves behind is also relatively small, usually only 5 to 20 times the mass of our Sun. If you want a 40 billion solar mass giant, starting with a 10 solar mass seed is like trying to build a skyscraper starting with a single grain of sand. The Eddington limit acts like a speed limit on the construction crew, ensuring they can only add a few more grains every 1,000 years. But what if you could skip the star entirely? Scientists call this the vortex mystery, or more formally, direct collapse. It is a scenario where the universe essentially cheats the laws of stellar evolution to create a monster from scratch. Imagine you are standing in the early universe, just a few 100 million years after the Big Bang. The cosmos is filled with enormous pristine clouds of hydrogen and helium gas. Normally, as these clouds cool down, they start to fragment. Think of it like a giant ball of cookie dough being pulled apart into thousands of tiny pieces. Each of those pieces eventually collapses to form an individual star. This is how galaxies like our Milky Way were built. But in the unique high-pressure environment of the early universe, something else could happen. If a gas cloud is massive enough, and if it is being kept warm by the radiation of nearby galaxies, it might never fragment. Instead of breaking into 1,000 tiny stars, the entire cloud begins to act as a single, unstable unit. It doesn't become a star because it is too large and moving too fast for nuclear fusion to ever find its footing. Instead, the entire disk of gas begins to swirl. This is where the analogy becomes something you have seen in your own home. Imagine you are standing over a bathtub filled to the brim with water. As long as the plug is in, the water is still. It is a massive, heavy volume of liquid, but it isn't doing much. But the moment you pull the plug, everything changes. The water doesn't just fall down the drain, it forms a vortex. The rotation concentrates the energy and the mass into a single, narrowing point. The further the water gets toward the centre, the faster it spins, and the more force it exerts on everything around it. In a direct collapse scenario, a gas cloud the size of a small galaxy acts like that bathtub water. There is no star phase where the gas is slowly processed into sunlight. Instead, the entire mass of the cloud, hundreds of thousands of suns worth of material, flows directly into the centre in a massive, swirling torrent. The plug in this cosmic bathtub is the point where the density becomes so high that the fabric of space-time itself simply snaps. The result is a direct collapse black hole. This is not a stellar corpse. It is something entirely different. While a normal black hole starts its life at 10 or 15 solar masses, a direct collapse seed starts its life at 100,000 times the mass of the Sun. Let's humanize that number. If a standard stellar mass black hole is a single marble in the palm of your hand, a direct collapse seed is a sphere of lead the size of a house, and it starts at that size on day one. This seed has skipped millions of years of growth. It has bypassed the Eddington limit by simply not existing as a growing object. It was born already massive. From this starting point, reaching the scale of the early giants is no longer a mathematical impossibility. It is simply a matter of a few 100 million years of aggressive feeding, which the data tells us is exactly what happened. This mystery is one of the most significant credibility anchors in modern astrophysics, because it shifts our view of black holes from being byproducts of stars to being the architects of the universe. For a long time, we thought galaxies formed first, and then black holes grew inside them. But the direct collapse theory suggests the opposite might be true. It suggests that these massive vortex black holes were the very first things to form, and their immense gravity acted like a scaffold that pulled the rest of the gas and stars together to build the galaxies we see today. We are looking at a universe that may have been seeded with giants before the first light of a traditional star ever touched the darkness. This realization carries a quiet, measured weight. It means that when you look at the centre of our own galaxy, at the 4 million solar mass giant known as Sagittarius A star, you aren't just looking at a hole in space. You might be looking at the very reason the Milky Way exists at all. But if direct collapse explains how they got so big, it doesn't explain what happens once you actually fall inside one. And it doesn't explain the terrifying reality that once you cross the horizon, your geography disappears and your future becomes a single, unavoidable date with a singularity. To understand that, we have to move from the mystery of birth to the mystery of the time-space flip. If you are finding this investigation into the cheating mechanics of the early universe as fascinating as I do, make sure you are subscribed. We are moving deeper into the horizon now, to a place where space and time no longer mean what you think they do. The investigation continues with the date with destiny. As we move from the violent swirling birth of the early giants and the direct collapse vortex, we find ourselves standing at the edge of the most significant boundary in nature. You have likely heard the term event horizon, described as a point of no return. In popular culture, it is often portrayed as a physical gate, or perhaps a waterfall in space, where gravity simply becomes too strong to swim against. But the reality, as established by the data and the mathematical foundations of general relativity, is far more unsettling. To understand the fourth mystery on our list, you have to leave behind your intuition about what space and time actually are. You have to prepare for a transition that scientists call the time-space flip. Imagine you're in your ship, positioned just a few miles outside the shadow of a stellar mass black hole. From this vantage point, everything looks like a masterpiece of distorted light. Because the black hole's gravity is so extreme, it is bending the light of the stars behind it, wrapping them into a glowing ring that scientists call gravitational lensing. If you look closely enough at the edge, the warping becomes so severe that a beam of light could actually travel in a full circle around the hole. You could, in theory, look straight ahead and see your own back. But you aren't here for the view. You are here to cross. As you begin your descent, a strange divergence occurs. If someone were watching you from a safe distance, perhaps a colleague on a support ship, they would never actually see you cross. Because gravity slows down the vibration of light and the ticking of clocks, your colleague would see you move slower and slower as you approach the horizon. To them, you would appear to freeze at the edge, your image growing redder and dimmer until you simply faded into the infrared background of the universe. But for you, the person inside the journey, nothing feels frozen. You check your watch and it ticks perfectly. You feel your pulse, and it is steady. You cross the event horizon without a bump or a flash of light. From your perspective, The horizon is not a wall. It is just a coordinate in space. However, the moment you cross that invisible line, the universe as you know it is deleted. This is not speculation. This is the direct result of the Schwarzschild metric, the mathematical solution to Einstein's equations that describes the geometry of a black hole. When you are outside the black hole, the math treats space, your position, and time, the ticking of your clock, as distinct things. You have freedom in space. You can move left, right, up or down, but you are a prisoner of time. You cannot stop yourself from moving into the future. But according to the equations, something bizarre happens the moment you pass the Schwarzschild radius. In the metric that defines your reality, the signs flip. The coordinate dr, which represents your radial distance or space, and the coordinate dt, which represents time, effectively swap roles. Inside the horizon, space becomes time and time becomes space. To humanize this abstract flip, imagine you are walking down a hallway. Outside the black hole, the hallway is space. You can walk forward, you can stop, or you can turn around and walk back the way you came. Time, meanwhile, is the wind at your back, pushing you forward at 1 second per second. You can't turn around in time. But once you cross the horizon, the hallway itself is no longer space. The hallway has become time. This leads us to the most existential mystery in physics. The singularity is not a place you travel to. It is a date in your future. Think about your life right now. You might be worried about a meeting you have next Tuesday. You can move to a different city. You can hide in a basement, or you can fly to the other side of the planet, but you cannot move away from next Tuesday. It is a moment in time, and it is coming for you whether you like it or not. Inside a black hole, the centre, or the singularity, is exactly like that Tuesday. It is no longer a location in space that you are falling toward. It has become a point in time that you are aging toward. The reason you cannot escape a black hole is not just that the gravity is strong. It is that every possible path you take and every direction you turn leads only to the future, and in that specific region of the universe, the singularity is the future. To move away from the centre of a black hole would be as logically impossible as trying to move away from tomorrow. This realization shifts the mystery from a mechanical problem to a philosophical one. When you are inside, you actually gain a strange kind of freedom over what used to be time. You can move forward or backward in that dimension, but it doesn't help you. Because the dimension of space, the one that leads to the exit, has become a one-way street of time that only leads deeper in. This is the date with destiny. It is a place where your geography has been stripped away and replaced with a countdown. Scientists are still stumped by the implications of this flip. If space and time can trade places, what does that say about the true nature of the fabric of our universe? Is the flow of time we feel every day just a local illusion that can be reconfigured by enough mass? As we sit here in the quiet stillness of our rooms, it is measured fact that we are currently moving through a version of space-time where we have agency over our position. We can get up and walk to the kitchen, but there are regions of our own galaxy, confirmed real places, where that agency is physically impossible, where moving to the kitchen would be as impossible as moving to the year 1995. The investigation into the horizon doesn't just challenge our technology, it challenges our definition of free will. It suggests that under the right conditions, the very concepts of here and now can be turned inside out. But if the horizon is this strange, if it is a place where the laws of time itself are rewritten, then we have to ask a terrifying question. If you were actually falling through this flip, would the boundary even let you pass through in one piece? Or does the very nature of this transition create a wall of fire that destroys anything that touches it? This leads us to the next mystery in our investigation, a paradox that has split the physics community for decades. The investigation continues with the firewall paradox. We have reached the midpoint of our investigation, and here, at the very edge of the darkness, we encounter a problem that does not just challenge our technology, it challenges our sanity. Up until this moment, we have treated the event horizon as a mathematical boundary, a coordinate in space where the rules of time and space perform a bizarre, inverted dance. We have spoken about it as an invisible line that you would simply sail through, perhaps without even noticing that your reality had been deleted. But there is a growing, violent disagreement at the heart of modern physics. It is a conflict between the two most successful theories we have ever devised, and it centres on a single terrifying question. Does the event horizon have a surface? To understand the fifth mystery on our list, you have to understand the character of the man who first defined these objects. Albert Einstein's greatest gift was his ability to visualise the universe through simple, domestic scenarios. He didn't just look at equations. He imagined himself as a participant in the phenomenon. One of his most famous thought experiments involved an elevator. He realised that if you were inside an elevator in deep space and the cable snapped, you would float. For as long as you were falling toward the Earth, you would feel weightless. You wouldn't feel the pull of gravity because you were becoming part of the fall itself. Einstein called this the happiest thought of my life, and it became the foundation of general relativity. Applying this to a black hole, Einstein's math is very clear. If you are falling toward a supermassive black hole, the event horizon would be a non-event. Because the hole is so large, the tug on your feet wouldn't be significantly stronger than the tug on your head yet. You would look around, check your pulse, and see nothing but the distorted light of the stars. You would sail through the horizon smoothly, experiencing what physicists call no drama. To Einstein, the horizon is not a wall, it is just a shadow. But there is another side to this story. There is a second titan of physics that has never quite gotten along with Einstein, quantum mechanics. While general relativity is the physics of the very large, planets, stars and galaxies, quantum mechanics is the physics of the very small. It governs the behaviour of atoms, electrons and the invisible fields that make up the vacuum of space. And in the quantum world, there is one rule that is more sacred than any other. Information can never be destroyed. Let's humanise that concept because it sounds abstract. Imagine you have a book. If you burn that book in a fireplace, you might think the information is gone. But according to the laws of physics, if you were a super being with a powerful enough computer, you could collect every atom of ash, every molecule of smoke, and every photon of heat released by the fire. In theory, you could use that data to reconstruct the book perfectly, word for word. The universe, at its most fundamental level, has a perfect memory. It never forgets the state of a particle. This is where the mystery becomes a paradox. In the 1970s, Stephen Hawking discovered that black holes are not truly black. Because of a strange hissing noise in the quantum vacuum, black holes slowly leak energy. Tiny pairs of particles are constantly popping into existence at the very edge of the horizon. Usually they annihilate each other and vanish. But at the event horizon, one particle can fall in while the other escapes into space. This escaping energy is called Hawking radiation. Over trillions upon trillions of years, a number of years so large it makes the current age of the universe look like a single heartbeat. This radiation causes the black hole to melt. It loses mass until eventually the black hole evaporates and disappears entirely. And this is the death of Einstein moment. if you fall into a black hole carrying all the information of your life, your DNA, your memories, the atoms that make up your body, and the black hole later evaporates into thermal radiation that contains no information, where did you go? If the information is gone, then the laws of quantum mechanics are wrong. But if the information is preserved, then Einstein's smooth entry must be a lie. This is the firewall paradox. In 2012, a team of 4 physicists, often referred to as AMPS, proposed a radical and unsettling solution. They argued that if information is truly preserved, it cannot fall into the black hole. It must stay at the edge. But for the information to stay at the edge while you sail through, the laws of physics would have to clone you, and the universe forbids cloning. The only way to resolve the conflict, they suggested, is if the no-drama rule is false. They proposed that the event horizon is not an invisible line. Instead, it is a firewall. They suggested that the moment you touch the horizon, you wouldn't sail through smoothly. You would hit a wall of searing, high-energy quantum particles that would incinerate you instantly. Your atoms wouldn't be swallowed, they would be scorched and smeared across the surface of the hole. This is the central conflict of modern science. Einstein says you feel nothing. Quantum mechanics, in its most modern interpretation, says you are deleted by a wall of fire. This is not speculation. This paradox has split the physics community right down the middle for over a decade. It is a recorded, measured breakdown in our logic. If Einstein is right, the very foundation of quantum reality is broken. If the firewall is real, then Einstein's greatest masterpiece, general relativity, fails at the very place it was meant to shine. Imagine finding a set of blueprints for a house where the kitchen is designed by one architect and the living room by another. Individually, the rooms are perfect. But when you look at the doorway between them, the floors are at different heights, and the walls don't meet. The event horizon is that doorway. It is the place where our 2 best maps of reality refuse to line up. When you look at a picture of a black hole, like the glowing orange donut of Sagittarius A star or M87, you are looking at more than just a gravitational trap. You are looking at a battleground. You are seeing the place where the measured certainty of our world meets an unexplained contradiction that we may not have the brain power to solve yet. We are currently living in a window of time where we have detected the chirp of black holes colliding and seen the shadow of their horizons. We can measure their mass, their spin, and their charge, but we are still standing on the outside, looking at a door that we cannot open without breaking the laws of the universe. The firewall is the ultimate gatekeeper. It suggests that the universe may have a security system designed to prevent us from ever seeing the broken physics inside. It is a censorship of the most violent kind. But what if there is a third option? What if the information isn't burned at the surface, but stored there in a way that doesn't require a wall of fire? What if the black hole isn't a 3D volume at all, but a 2D memory? To understand that, we have to move from the heat of the firewall to the cold mathematical beauty of the holographic memory. If you are finding this investigation into the searing contradictions of our reality as fascinating as I do, make sure you are subscribed. We are moving from the death of Einstein to the realization that the entire universe might be an illusion. The investigation continues with the holographic memory. We have arrived at a point in our investigation where we must confront a possibility that sounds like the plot of a science fiction film. Yet it is currently the leading mathematical solution to the survival of our reality. In the previous chapter, we stood at the edge of the firewall, a wall of searing energy that suggested the laws of Einstein must fail to satisfy the laws of the quantum world. It presented a violent choice. Either you sail through the horizon and the universe loses its memory, or you are incinerated by a wall of fire so that the information of your existence can be preserved. But what if there is a third option? What if the information of your life, the arrangement of your atoms, the specific electrical signals of your memories, the very blueprint of who you are, is not destroyed by fire or lost in a singularity? What if instead it is simply moved? To understand the sixth mystery on our list, we have to explore the cold, mathematical beauty of the holographic memory. To grasp the weight of this mystery, we must first remind ourselves of the sacred rule we discussed earlier. In the quantum world, information is never truly destroyed. Let's look at this through a concrete domestic analogy provided by the data. Imagine you are standing in front of a fireplace with a book. If you throw that book into the flames, you might assume the information within its pages is gone forever. But according to the laws of physics, the universe has a perfect memory. If you were a super being with a powerful enough quantum computer, you could, in theory, collect every single atom of ash, every drifting molecule of smoke, and every tiny photon of heat released by that fire. With that data, you could mathematically reconstruct the book, word for word, cover to cover. The information was never deleted. It was only scrambled. However, for decades, black holes seem to be the only places in the cosmos that actually burned the book and deleted the ashes. If you fall into a black hole and it eventually evaporates through Hawking radiation, that radiation was thought to be thermal, meaning it was just random featureless heat that contained no record of what fell in. This created the information paradox. It suggested that if you jumped into a black hole, you would be erased from the universe, breaking every law of physics we have ever written. The solution that emerged is as startling as it is elegant: the holographic principle. This principle suggests that all the information about the three-dimensional objects that fall into a black hole is not actually lost in the interior. Instead, it is imprinted onto the two-dimensional surface of the event horizon. Think of it like this. When you walk toward the horizon, you feel like you are moving through 3D space. But as far as the universe's accounting system is concerned, as you cross that line, your 3D data is smeared across the 2D surface area of the hole. This leads us to a concrete analogy that you likely have in your pocket right now. Look at the holographic sticker on a credit card or a high-security ID. When you tilt the card, you see a three-dimensional image with depth and perspective. But that image isn't inside the card. The 3D image is a projection. All the data required to create that 3D experience is actually encoded on a flat, two-dimensional piece of plastic. The holographic principle suggests the event horizon works exactly like that sticker. To an observer outside, the black hole is not a 3D pit or a volume of space. It is a 2D surface that acts as a repository for every bit of information that has ever crossed its boundary. This isn't just a clever metaphor, it is supported by the measured relationship between entropy and surface area. In standard physics, the amount of information you can fit in a room depends on the volume of that room, how much 3D space is inside. But for black holes, the math is different. The entropy of a black hole, the measure of how much hidden information it contains, is proportional to its surface area, not its volume. Let's humanize that mathematical fact. If you have a black hole that eats a star, the event horizon must grow. But it doesn't grow to make room inside for the star. It grows its surface area to provide more pixels on the boundary to store the star's data. It is as if the universe is telling us that the 3D interior of the black hole is an illusion, and the only part that is real or measured is the 2D shell. This realization led to a concept called black hole complementarity. It is the idea that no single observer can ever see the information in two places at once. If you are the person falling in, you see yourself inside the 3D volume, heading toward your date with the singularity. But to a colleague watching from far away, you never appear to enter. You are simply flattened onto the 2D horizon, becoming part of the permanent record of the whole. Because the laws of physics prevent you from ever communicating again, the universe allows these two versions of reality to exist simultaneously without a conflict. This is the stretched horizon, a 2D boundary where the information stays in a space where light still exists, avoiding the paradox of the singularity. If this principle holds true for black holes, the implications for our own existence are profound. Many physicists now speculate that if a black hole stores information this way, perhaps the entire universe does too. We may live in a 3D world, moving through 3D rooms and drinking from 3D cups, but we could actually be a holographic projection of data stored on a distant 2D boundary at the edge of the cosmos. The mystery scientists can't fully explain is why the universe would choose to store its most complex data in such a simplified way. Why does the surface area matter more than the depth? We are currently in a measured window of time where we are building the tools to test this. If we can gather all the Hawking radiation from a dying black hole over trillions of years and process it through a giant quantum computer, we might actually be able to reconstruct what fell in. As physicist Brian Cox noted, in a very real sense, you would come out. This is the cold mathematical beauty of the holographic memory. It suggests that nothing is ever truly gone. It is just waiting to be read from the surface. But even if the information is stored on the surface, we still have a problem with what lies beneath. If the singularity isn't a point of infinite density, then what is it? What if we have been calling these objects black holes when they are actually something else entirely, cosmic imposters that don't have horizons at all? To understand that, we have to move from the 2D surface to the possibility that black holes aren't even holes. If you are finding this investigation into the holographic nature of our reality as fascinating as I do, make sure you are subscribed. We are moving deeper into the structure now, toward the cosmic imposters. The investigation continues with fuzzballs and gravastars. Every time we have used the word black hole in this investigation, we have been using a placeholder for a failure. In the language of physics, a black hole is often defined by its centre, the singularity. This is described as a point of infinite density where an entire star's worth of mass is crushed into zero volume. But there is a secret that many physicists only discuss in hushed, measured tones. Infinite is not a physical description. It is a warning. In any other field of science, if your equations result in an infinity, it is a signal that your math has broken. It is the cosmic equivalent of a divide by zero error on a calculator. It means the map we are using no longer matches the territory. This leads us to the seventh and perhaps most radical mystery on our list. What if the reason we can't explain the singularity is because the singularity does not exist? Scientists are currently exploring a series of models known as regular black holes. The goal of these models is something called regularization, an attempt to tweak the equations so the math stays regular and never veers off into the impossible territory of infinity. This process has revealed a trio of cosmic imposters, objects that, from a distance of millions of miles, look and act exactly like the black holes we've confirmed in our data, but up close are revealed to be something else entirely. The first and most prominent candidate comes from the world of string theory. Scientists call them fuzzballs. To understand a fuzzball, you have to look past the idea of particles as tiny points or billiard balls. In string theory, every fundamental piece of the universe, every electron, every quark, every photon, is actually a tiny vibrating loop of the string. Just as the different vibrations of a guitar string create different notes, the different vibrations of these cosmic strings create the different particles of our reality. In the standard model of a black hole, matter falls into the centre and is crushed into a point of nothingness. But a fuzzball suggests that matter cannot be crushed that far. Instead, as the strings are packed tighter and tighter together, they begin to overlap and entangle. They don't fall into a hole. They weave themselves into a dense, solid and incredibly complex ball of quantum string. Imagine you are looking at a ball of yarn from across a large room. From that distance, it looks like a solid, dark sphere. You might even mistake it for a hole in the carpet. But as you get closer, as you reach out and touch it, you realise it isn't a hole at all. It is a quantum thicket. It is a messy, vibrating, 3D tangle of strings and membranes. This imposter solves the two biggest headaches in physics in one fell swoop. First, it gets rid of the singularity. Because the strings have a physical size, they can only be packed so tightly before they push back. There is no point of infinite density. There is only the dense, vibrating mass of the fuzz. Second, it solves the information paradox. Because there is no interior or hole, the information of whatever fell in isn't lost in a singularity. It is simply stored and entangled within the intricate internal structure of the strings themselves. To you, the observer, a fuzzball would look like a conventional black hole. It would still have the same mass, the same spin, and it would still warp the light of the stars behind it into a glowing ring. But the shadow you see isn't an empty pit. It is the surface of a solid quantum object that is constantly absorbing and re-emitting radiation. But if fuzzballs are too messy for your intuition, there is a second, cleaner imposter that scientists have conjured up, the gravastar, or gravitational vacuum star. To grasp the concept of a gravastar, we have to talk about the energy of nothingness. You have likely heard that the universe is expanding, but the mystery is how. Scientists speculate that there is a force driving this expansion called vacuum energy. This is energy intrinsic to the fabric of space-time itself. It is a repulsive force. It pushes outward. A gravastar is what happens if you take a bubble of this repulsive vacuum energy and wrap it in a shell of matter. Imagine you are holding a soap bubble. The air inside the bubble is pushing outward, trying to expand, while the surface tension of the soapy water is pulling inward, trying to keep it contained. A gravastar exists in that same kind of violent equilibrium. At its core is a region of dark energy that pushes outward with such ferocity that it prevents the matter from ever collapsing into a singularity. This outward push acts like a cosmic jack. Imagine you're working under a car and you use a hydraulic jack to keep the vehicle propped up. Gravity is the weight of the car pushing down. The vacuum energy is the jack pushing back up. The result is an object with an ultra-thin, incredibly dense shell of matter, a gravitational membrane surrounding a core of pure repulsive space. Like the fuzzball, a gravastar has no hole. There is no event horizon from which light can never escape. Instead, there is just a physical surface that is so dense and so warped that it looks like a horizon from the outside. It would have no singularity and no paradoxes. It would be a solid, if bizarre, addition to the family of stars. Some researchers have even suggested a more elaborate version of this imposter called knee stars, which are essentially gravastars trapped inside other gravastars, like a set of cosmic Russian nesting dolls. And the existence of these imposters, fuzzballs and gravastars, is one of the most significant credibility anchors in our investigation. This is not speculation. These are the actual mathematical blueprints that respected physicists have put forward to save the laws of nature from the infinity of the singularity. From where you are sitting right now in the measured safety of your room, these objects seem like mathematical curiosities, but in the deep sky they represent a fundamental question of identity. When we point our telescopes at Sagittarius A star, are we looking at a hole that deletes reality, or are we looking at a solid, vibrating quantum surface that is simply too dark for us to see? The cosmic imposters suggest that the universe may be more solid than we think. They imply that nature has a way of avoiding the divide by zero error, even in its most extreme environments. They suggest that there are no dead ends, only surfaces we haven't yet learned how to touch. But if these objects have solid surfaces, if they don't have clothes to hide their interiors, then we have to ask about the most forbidden possibility of all. What if a black hole spins so fast that it sheds its event horizon entirely, leaving its broken physics completely exposed to the rest of the universe? This leads us to the next mystery, the one that scientists call the uncensored truth. If you are finding this investigation into the imposters that hide at the centre of our galaxy as fascinating as I do, make sure you are subscribed. We are moving from the solid surfaces of fuzzballs to the regions where the universe's security system fails entirely. The investigation continues with the naked singularity. Throughout our investigation, we have treated the event horizon as the ultimate antagonist of the cosmos. We have described it as a wall of fire, a holographic memory bank, and a point where the very geography of your life is replaced by a date with destiny. In every model we have explored, the horizon is the clothes that the black hole wears, a dark, featureless cloak that hides the broken physics of the singularity from the rest of the universe. But we must now confront the eighth, and perhaps most disturbing, mystery on our list. We have to ask if it is possible for a black hole to get caught in a state of cosmic undress. Scientists call this the mystery of the naked singularity, and it represents what might be described as the uncensored truth of our reality. To understand how a black hole could shed its clothes, we first have to talk about something that nearly every black hole in the universe is doing right now: spinning. In the early days of black hole theory, we mostly studied static black holes, objects that simply sat there, heavy and silent. But the data has since confirmed that the universe is far more dynamic. When a massive star collapses, it doesn't just fall straight down, it brings its rotation with it. Just as an ice skater spins faster when they pull their arms in, a collapsing star accelerates its rotation to a dizzying degree as it shrinks. The result is what is known as a Kerr black hole, a rotating monster that does something to the universe that defies human intuition. Imagine you are standing in a large vat of thick molasses. If you start to spin around very fast, you won't just move through the molasses, you will start to drag the molasses around with you. A spinning black hole does this to the very fabric of space and time. This is a measured phenomenon called frame dragging. It means that near a spinning black hole, space itself is being twisted like taffy. You could not stand still even if you had the most powerful engines ever built, because the ground you are standing on, the vacuum of space itself, is rushing in a circle at hundreds of millions of miles per hour. The speed of this rotation is staggering. Some black holes have been confirmed to spin at over 80% the speed of light. Now, here is the complication. When any object spins, it experiences centrifugal force, the outward push that makes a spinning ball of pizza dough flatten into a disk. In a black hole, there is a violent tug-of-war happening. Gravity is trying to pull everything inward toward a single point, while the sheer velocity of the spin is trying to throw everything outward. According to the mathematical solutions of general relativity, if you could somehow make a black hole spin fast enough, the centrifugal force would begin to win. The event horizon, the security system that hides the singularity would start to bulge at the equator. It would stretch and thin. And if you push that spin past a critical mathematical limit, the equations suggest the horizon would simply vanish. The result is a naked singularity. It is a point of infinite density, a place where the laws of physics have visibly broken and veered off into infinity, but with no horizon to cover it up. It is the heart of the storm, standing completely exposed to the rest of the galaxy. To humanize why this is so unsettling, imagine you are using a computer. Every now and then, a program might crash. You get a blue screen, or the window freezes. This is a singularity in the code, a place where the logic has broken down. But because you have an operating system, that crash is contained behind the screen. It doesn't affect your physical desk or the air in your room. A standard black hole is like that crashed program. The broken physics is contained behind the event horizon. You can't see it, and its infinite contradictions can't leak out to affect the rest of the universe. But a naked singularity is a computer crash that doesn't stay on the screen. It is a place where the broken logic of the universe is physically present in the room with you. Because there is no horizon to act as a barrier, the infinite gravity and the shattered laws of causality at the centre could, in theory, radiate outward and affect the stars, the planets, and even the atoms of your own body. This leads us to the why that haunts modern astrophysics. Why have we never seen one? In 1969, the physicist Roger Penrose proposed a radical idea called the cosmic censorship hypothesis. He argued that the universe appears to have a no-nudity policy. He suggested that there is a fundamental law of nature, one we haven't fully written down yet, that prevents naked singularities from ever forming. In Penrose's view, the universe conspires to hide its own contradictions. It demands a censor in the form of an event horizon to shield the rest of reality from the places where physics fails. This is one of the most profound law gaps in the source material. We don't know why the universe would care about being censored. Is it because a naked singularity would destroy determinism, the ability to predict the future based on the past? If a naked singularity were exposed, anything could theoretically come out of it at any time without a cause. The universe would stop being a place of logic and start being a place of pure unpredictable chaos. This is not speculation. Multiple independent teams have run simulations trying to force a black hole to shed its horizon by overspinning it or throwing in specifically charged particles. So far, the universe seems to push back. Every time a black hole gets close to that naked limit, something happens to prevent it. It might stop eating, or it might radiate away its spin. But so far is not the same as never. Somewhere in the deep, dark spaces between the galaxies, there could be a monster that has already broken the rules. A place where you could look through a telescope and see, not a shadow or a ring of light, but the uncensored truth. A point where the fabric of reality has been ripped wide open and the infinite error at the heart of the universe is staring right back at you. The mystery of the naked singularity reminds us that our measured world is protected by boundaries we didn't create and don't fully understand. We are like children living in a house where certain doors are permanently locked for our own safety. We have spent our history studying the wood of the doors, but the naked singularity is the terrifying possibility that one of those doors might one day swing open, revealing that the house of our universe doesn't actually have a floor. If you are finding this investigation into the censored regions of our reality as fascinating as I do, make sure you are subscribed. We are moving from the exposed secrets of the present toward a mystery that suggests black holes are even older than the universe itself. The investigation continues with the ghost in the machine. We are now approaching the most profound and perhaps the most unsettling mystery in our investigation. Up until this point, we have treated the Big Bang as the ultimate time zero, the moment when everything from the atoms in your body to the stars in the deepest reaches of the sky was born out of a single hot, dense point. We have been taught that the Big Bang is the beginning of the story, and that asking what happened before it is as logically impossible as asking what is north of the North Pole. But there is a secret hidden in the math of black holes that suggests our beginning might actually be a middle. To understand the 9th mystery on our list, you have to look past the light of the stars and peer into the very oldest record we possess, the cosmic microwave background, or the CMB. Imagine you are looking at a baby picture of the universe. This light was born roughly 380,000 years after the Big Bang, a mere heartbeat in cosmic history. It is a faint ancient glow that covers the entire sky, and for decades we believed it was almost perfectly uniform. But when we looked closer, we found tiny ripples, small variations in temperature that eventually grew into the galaxies and star clusters we see today. However, there are smudges on this baby picture that shouldn't be there. In 2019, Sir Roger Penrose, a man who spent his life deciphering the math of black holes alongside Stephen Hawking, published a measured, peer-reviewed paper that challenged the very foundation of our history. He and his team identified several anomalies in the CMB sky that he believes are the ghosts of supermassive black holes that existed before our universe even began. He calls them Hawking points. To understand how a black hole could be older than the universe, we have to talk about the scale of their survival. We have already established that supermassive black holes are the giants of our cosmos, containing the mass of millions or even billions of suns. But their most terrifying power isn't their size, it is their longevity. As we discussed earlier, Stephen Hawking predicted that black holes slowly leak energy through a process called Hawking radiation. But this is not a fast process. For a supermassive black hole at the centre of a galaxy, the melting process is so slow that it would take longer than the current age of the universe to even begin to shrink significantly. If our universe is 13.8 billion years old, a supermassive black hole might live for trillions upon trillions of years. This creates a chronology gap that defies human intuition. It means that while every star in our galaxy will eventually burn out and every planet will crumble to dust, the supermassive black holes will still be there, sitting in the silence of a cold, dead universe. Penrose's theory, known as conformal cyclic cosmology, suggests that the universe goes through cycles, or aeons. He argues that when a universe becomes old, cold and empty, the very concepts of distance and time start to lose their meaning because there is nothing left for them to measure. At this point, the end of the old universe becomes mathematically identical to the beginning of a new Big Bang. But in this transition, the supermassive black holes are the only things that don't get deleted. Think of it like a sheet of paper that has been stamped with a heavy ink-soaked seal. If you take that paper and soak it in water until the fibres break down and you pulp it into a new sheet, the original message is gone. But if the stamp was powerful enough, it leaves a dent, a permanent scar in the texture of the fibres that can still be seen if you hold the new sheet of paper up to the light. The Hawking points are those dents. As a black hole from the previous aeon slowly evaporated over trillions of years, it released an immense amount of Hawking radiation into a single concentrated point. When the old universe reset and our Big Bang occurred, that concentrated point of energy survived the transition. It became a highly energetic anomaly that influenced the way the matter in our young universe began to huddle together. This is not speculation. Penrose and his team claim to have found evidence of these specific anomalous spots in our own sky, regions where the temperature ripples are far more energetic than random chance should allow. They are, in a very real sense, the ghosts in the machine of our reality. If this theory is correct, it means that our supermassive black holes, like Sagittarius A star at the centre of the Milky Way, might be the survivors of a previous reality. It means they are not just objects in our universe. They are the scaffolding upon which our universe was built. The scale of this realization carries an immense existential weight. Humanized, it means that when you look at a photograph of a black hole, you might not be looking at a product of the Big Bang. You might be looking at a bridge between cosmic aeons, a monument that has stood since before time itself was reset. We are currently living in a measured window of time where we have the technology to see these scars in the ancient light of the sky. We are the first generation of our species that can even ask the question, are we the first people to inhabit this cosmos? Or are we just the latest tenants in a house that has been rebuilt 1,000 times over? The mystery scientists can't fully explain is why some information, the specific memory of a black hole, is allowed to survive when everything else is destroyed. This forward momentum leads us to our final mystery. If black holes can survive the end of a universe, where does that information eventually go? Does it simply wait in the dark, or does it do something even more radical, birth an entirely new reality of its own? The investigation continues with the final evaporation. We have traced the life cycle of these monsters from their violent births in the hearts of collapsing gas clouds to their roles as the silent architects of entire galaxies. We have explored the places where time becomes space, and where the laws of physics are stripped naked or hidden behind walls of fire. But every investigation must eventually confront the end of the story. And for a black hole, the end is not a bang, but a very long, very quiet evaporation. To understand the final mystery on our list, you have to look past the current age of the universe. You have to imagine a time so distant that the stars we see tonight have all burned out, their embers cooled to black cinders. The galaxies have drifted so far apart that they have fallen over each other's cosmic horizons, leaving every region of space in total isolation. In this era, the universe is a cold, dark, and hollow place. The only residents left are the black holes, the ultimate survivors. But even they are not permanent. This is the mystery of the final evaporation. In the 1970s, Stephen Hawking made a prediction that changed our understanding of the vacuum itself. He realized that empty space is not actually empty. On a quantum level, it is a hissing sea of activity where pairs of particles, one matter, one antimatter, are constantly popping into existence, only to instantly collide and annihilate each other. It is a measured, established phenomenon of the quantum world. But when this happens at the event horizon, the symmetry is broken. Imagine you are standing at the edge of a cliff. A pair of twins appears. One twin falls over the edge into the abyss, while the other is left standing on the solid ground. Because the twin that fell into the black hole carries negative energy to balance the universe's books, the black hole actually loses a tiny infinitesimal amount of its mass. The twin that escaped flies away into space as a single particle of light. This is Hawking radiation. It is the black hole leaking its mass back into the universe, one particle at a time. Scientists describe it like a block of ice melting in the sun, but the scale of this melting is what defies human intuition. Let's humanize the numbers, because at this scale, the zeros represent a duration that makes our entire history look like a flicker of a match. A stellar mass black hole, just 10 times the mass of our Sun, will take roughly 10 to the power of 67 years to evaporate. That is a 1 followed by 67 zeros. If you were to represent the current age of the universe, 13.8 billion years, as a single drop of water, the time it takes for a black hole to evaporate would fill all the oceans on Earth billions of times over. For the supermassive giants we discussed earlier, the ones with 40 billion solar masses, the clock is even slower. They will endure for 10 to the power of 100 years. This is a number so large that if you tried to write it out on a piece of paper, the paper would need to be longer than the observable universe. For almost the entirety of its life, the black hole is the most stable thing in existence. It is the only object capable of outlasting the stars. But as it radiates, it gets smaller. And as it gets smaller, it gets hotter. In its final moments, the black hole begins to shrink faster and faster, its temperature skyrocketing to quadrillions of degrees. Then, in one final silent flash of gamma rays, it vanishes. And this is where the mystery becomes a crisis. When that final flash occurs and the black hole is gone, what happens to the information? What happens to the billions of stars it ate? What happens to the holographic memory we discussed that was stored on its surface? If the black hole simply disappears, then the universe has committed the ultimate crime in physics. It has deleted its own history. This is not speculation. This is the information paradox in its final, most urgent form. If the information is gone, the laws of the quantum world, which state that information is eternal, are fundamentally broken. But there is a resolution that many respected physicists, including Lee Smolin, are currently debating. It is a theory that suggests the black hole doesn't just end, it births something else. This is the concept of the baby universe. To understand this, we have to look back at the singularity. We have called it a dead end and a broken point in math. But what if the singularity is actually a seed? According to some models of general relativity, the intense warping of space and time inside a black hole doesn't just stop at a point. Instead, it creates an Einstein-Rosen bridge, a wormhole. In this scenario, the matter and information that fall into the black hole don't get crushed into nothingness. Instead, they are funneled through this bridge and emerge on the other side. But the other side isn't a place in our universe. It is a new, separate region of space-time, a baby universe that is physically disconnected from our own. Imagine you are blowing a soap bubble. As you blow, a small part of the bubble starts to bulge and eventually pinches off, floating away as its own independent sphere. Our universe might be the parent bubble, and every black hole we see in the sky is the pinch point, where a new baby universe is being born. This is a profound shift in the law of the cosmos. It suggests that the Big Bang of that new universe was the moment our black hole formed. It means that what we see as a destructive, terrifying hole is actually an act of cosmic reproduction. If this is real, it carries a startling implication for our own origins. If black holes birth universes, then it is mathematically probable that our own Big Bang, the start of everything you have ever seen or loved, was the result of a black hole forming in a parent universe that existed before ours. We are not the centre of reality. We are just one generation in a vast, sprawling family tree of universes, each born from the heart of a dying star in the one that came before. This is not science fiction. This is a legitimate hypothesis that attempts to explain why our universe's laws of physics seem so finely tuned for life. If universes that produce more black holes reproduce more often, then the cosmos would naturally evolve to be filled with the kinds of stars and gas that lead to black hole formation, the same conditions that allow planets and life to exist. As we reach the end of this investigation, we have to sit with the measured weight of these 10 mysteries. We live on a small, rocky planet orbiting a garden-variety star. We spend our lives worried about meetings, bills, and the small dramas of our daily existence. But just outside the thin veil of our atmosphere, the universe is performing a drama of a scale we can barely fathom. Black holes are the sentinels of that drama. They are the rogue predators drifting through our galaxy, the ancient giants older than the stars, and the gateways to realities we will never visit. They represent the ultimate limit of our knowledge, the place where our maps of reality end and the unexplained begins. But there is a final human-scale reflection that carries the most weight. In a trillion years, when the last star has gone dark and the galaxies are invisible to one another, the only thing that will remain of our era, the only hard drive that will still contain the record of the atoms that once made up your body and the light that once warmed your face, is the supermassive black hole at the centre of the Milky Way. It is the only object with a memory long enough to survive the death of the stars. It is the only thing that will remember we were here. We are small, we are transient, and the universe is enormous beyond all reason. But we are the species that looked into the darkness, measured the chirp of colliding giants, and dared to ask what was inside. The black hole may be a mystery we can't explain, but it is also the most interesting thing we have ever discovered. The investigation into the darkness is not a reason for dread. It is a reason for wonder, because as long as there is something we don't understand, there is a reason to keep looking up. The investigation is ongoing, and we are the ones doing it.